Hello. Today, I'd like to talk with you about algorithm performance. In today's lecture, we'll discuss why we analyze algorithm performance and how we go about doing it. Have you ever had those thoughts while coding? Huh, why is my program so slow? Why is someone else's code so much faster than mine? Today, we're going to uncover the secrets behind that. Here's a very simple problem. Add up all the numbers from 1 to n. You gave this problem to 3 of your friends, and each of them solved it in a different way. Your friend A did it honestly, adding each number from 1 to n one by one. And then there's your friend B, who's a bit odd. Instead of adding up the numbers from 1 to n exactly, B used something called J and calculated the sum from 1 to I. 3 means, in the end, you've added 1 3 times. This means you've added 1 2 times. So, in that way, you add up the numbers from 1 to n, and then you add that result. The third friend, C, is really smart. After thinking about the calculation, they realized that adding up the numbers from 1 to n is, in the end, always the same as multiplying n by n plus 1 and then dividing by 2. So they made and used this formula. Which of these 3 friends do you think would be the fastest? And just how big of a difference would that make? To find out how fast they are, I assumed n is 10,000 and actually measured the time it took using these 3 methods. So, how did the results turn out? Drum roll. Ta-da! Take a look at the results. Actually, there might be a bit of a difference between A and C, but they were so fast that they both just show as 0 milliseconds. These two didn't really have any time difference, but for B, even though the value was the same, it took 95 milliseconds. Wow. And that's with n being only 10,000. What if n was 100 million? So for B, I don't think it would have finished even by the time we got off work. Now, if you look here, the algorithms all look pretty similar, but this is A and this is B. And here, you can see how C did its calculation. Among the things added here, this part is code we included to calculate the time difference. So before starting, we record the time, and after it finishes, we record the time again to calculate the difference. So this part is included in the same way, but you can just think of it as code that's there to measure the time. Depending on which algorithm you choose, the program's execution time will change. This is called time complexity. Time complexity varies depending on the algorithm. When we think about the efficiency of an algorithm, we look at time and also consider something called space complexity. In other words, how much memory it uses. This is important too, but generally space complexity isn't considered that important because it doesn't increase that much. What do we usually focus on? Time complexity. I'll be explaining mainly about this today. How long will it take? When I run the program, how long will it take? Of course, besides the algorithm, there are various factors that affect speed. If we think about it in 2 main categories, We can say that it depends on two things: the software aspects that we control directly with code, and then the hardware aspects, meaning the environment where the program runs. Then people might ask this kind of question. Professor, computers have gotten really fast these days. Back in the day, there was Moore's Law, which said that semiconductor performance would double every 2 years. And now with cloud computing, things are really fast. So, can't we just use a good computer? That's something people might ask. That's a really good question, because hardware keeps advancing. But that doesn't mean we can just excuse ourselves by saying the algorithm is good, too. Because take a look at this graph. Here, the x-axis on the right represents the problem size, or the size of the input. And the vertical axis shows how long it takes. So, like algorithm A from earlier, when the time increases in direct proportion to the size of the input, we call this a linear algorithm, and those don't take very long. So as the input size grows, the time just increases linearly. But with algorithm B, when the time is proportional to the square of the size, proportional to the size squared, this is called a quadratic algorithm or a square algorithm, and as we saw earlier, these take a long time. So when you use this kind of algorithm, since the time increases in proportion to n squared, it can actually take much longer than you might expect. As the problem size gets bigger, you'll feel that it takes longer and longer. Even n squared already takes a long time, but what if you used an exponential algorithm? Well, honestly, you can only use it for really small cases, like less than 10 items. But as the numbers get bigger, if you actually implemented this kind of algorithm, I doubt even a supercomputer or even a supercomputer's grandpa could handle it. But with linear algorithms like this, even if you run them on the oldest computer in your house, they still work perfectly fine. That's why we need to consider the efficiency of algorithms. So, how can we measure this efficiency fairly? Earlier, I added some code to measure the time in that program, remember? Well, the thing is, if you do it this way, the performance varies from computer to computer, so the time will be different on each machine. And if you run it in the cloud, sometimes it takes less time, sometimes it takes longer, depending on the cloud environment. So measuring the time every single time like that isn't really accurate. Then how should we measure this? So developers made a sort of agreement. Instead of looking at how many seconds it actually takes, let's count how many times a basic operation is performed. Here, a basic operation means the core task of the algorithm. So, as the input size increases, we check the part that gets repeated the most. And by carefully looking at what this is directly proportional to, the total number of fundamental or basic operations performed according to the input size n is precisely what is referred to as the t and growth rate function, which describes its asymptotic behavior. In Korean, we could call this a growth rate function. So you can think of this as the number of basic operations for n. Shall we bring back our friends A, B, and C from earlier? Let's start with the fastest one, algorithm C. How many operations does algorithm C perform? First, one addition, then one multiplication, and one modulo division, just 3 operations in total. This has nothing to do with the size of n. Whether n is 100 or a million, it's still one addition, one multiplication, and one division. Those three operations never change. So, regardless of the value of n, the number of executions is fixed. We call this constant time. Now, let's move on to algorithm A. What's the basic operation of algorithm A? It's this one among these. Sum is updated by adding I to the current sum. So, if you look at this, how many times does it run? When I is 0, the body of the for loop doesn't execute, so that's 0 times. Then, when n is 1, it runs once. If n is 2, it runs twice, and so on. 3 means 3 times, and so forth. So, the value of t, n, and n are the same. So, as n increases, the number of operations increases steadily and proportionally. We call this linear time. The final algorithm we're going to analyze is algorithm B. The most important thing about algorithm B is that the for loop is repeated twice, and the number of repetitions is proportional to the given value of n. So if n is 0, it doesn't enter the loop anyway, so it's 0. But if n is 1, I repeats once, and j also repeats once. So I repeats once, and j repeats once. So in the end, t1 will be 1. Now, what happens if n is 2? If the value of n is 2, then when the variable I is equal to 1, the variable j repeats its iteration exactly once, and subsequently, when the variable I is equal to 2, the variable j repeats its iteration precisely twice. So I repeats twice. When n is 2, it repeats twice, but j repeats 3 times, so t becomes 3, because this addition happens 3 times. If you keep calculating like this, the value of t, n, is n times n plus 1 divided by 2. And here, the most important thing, the part that changes the most rapidly, is the value of n squared divided by 2. In other words, it requires n squared. We call this quadratic time. If you look at the graph, you can see that algorithm C stays flat and constant like this. It's laid out flat, and A increases in proportion to the value of n, but algorithm B shoots up to the sky in an instant. This is the difference in the size of the algorithm growth function, the growth rate function. Choosing an algorithm is kind of like picking a mode of transportation for your data processing journey. So think of the amount of data as the distance of the trip. In that case, algorithms that take constant, logarithmic, or linear time are very fast algorithms. So these kinds of algorithms work extremely fast, whether you have 10, 100, or even a million pieces of data. So whether it's a short or a long distance, you can think of them as supercars or KTX trains that finish in an instant. In contrast, algorithms with quadratic time complexity can be used, sure. These kinds of algorithms are actually used, but you have to be cautious when using them. Or if the problem is too large, they might not work very well. That's the idea. So for small data, well, even what we call small is probably bigger than you think. For example, with 1,000 data points, it calculates really fast. But if the number of data suddenly increases, oh, it takes a lot more time. It's kind of like walking from Seoul to Busan. Now, from here, the problem gets a bit more serious. If you go further, and the input size is proportional to the cube or even to an exponential function, then it's like a turtle walking. How long would it take to get from Seoul to Busan? Maybe about the 317th century. That's the kind of feeling we're talking about. So when there's only a small amount of data to process, everything might seem pretty similar. But as the amount of data increases, depending on which algorithm you choose, the arrival time could be just a few seconds, or it could take centuries. Well, to become a smart developer, you always need to think about what the fastest means of transportation is, or what the fastest algorithm is. So far, we've analyzed algorithms A, B, and C by counting the maximum number of basic operations they can perform. But what we really want to know is how long these algorithms actually take, right? We're not interested in guesses. We're interested in actual time. But as you'll see, counting every single line of source code or every single operator in an algorithm is way too complicated and tedious, and it also varies depending on how you implement it and on which computer you run it. We just want to get a rough idea of how fast something is, you know? So there's a more important method that comes into play. It's called asymptotic notation. There are three types of asymptotic notation. I'll explain how these notations differ by using the example of traveling from Seoul to Busan. Big O notation refers to the upper bound, or the worst case scenario. So, what this is saying is, how long do you think it will take to get from Seoul to Busan? Well, no matter how late it is, you'll arrive within 5 hours. It's similar to talking about it in this way. In reality, though, it might take less than 5 hours, maybe 4 hours, or if there's no traffic, you could even get there in 3 hours. But what we're guaranteeing is that it won't take more than 5 hours. That's the upper bound. Actually, this big O notation is the most commonly used notation in the fields of development and computer science. That's because what people care about most is when something will finish. And this notation guarantees that it will finish at least faster than this amount of time. So, among the algorithms we've used, roughly, algorithm B, this one is what we call big O of n squared, or big O of n to the power of 2. Big O of n squared. And then there's something called the big omega notation. This, on the other hand, is a lower bound. In other words, it assumes the best case scenario. So, how long does it take to get from Seoul to Busan? It's like saying, no matter how fast you go, it'll take at least 3 hours. What do you take the KTX or drive at dawn with no traffic? This sets the minimum time you can't go below. So, no matter how fast algorithm B is, it can't be faster than the speed of n squared. This too can be described as big omega of n squared. In Korean, we can say it's big O, omega of n squared. When we talk about big theta, it's the tightest way to describe it. This actually overlaps with both big O and big omega, meaning it takes at least 3 hours, but no more than 5 hours. So we know, then when going from Seoul to Busan, it must take between 3 and 5 hours. And especially when the upper and lower bounds are the same, that's when we use big theta, because it's the most precise expression. For example, in the case of algorithm B, it's n squared in big O as well. And from the perspective of big omega, it's also n squared. So in big theta, which is the intersection of the two, you can say it's big theta of n squared, or in other words, theta of n squared. you don't get it. If you're not sure, just remembering big O is enough. Other notations are rarely used. And you can think of your algorithm's worst case as at least being big O. So even though I explained it thoroughly, if you still don't understand, just remember that for the worst case, we use the big O notation. Still, let's go over each part one more time. In short, big O notation is a promise about performance. It guarantees at least this level of performance. It means that even in the worst case, this level of performance is guaranteed. So when we say big O of n squared or big O n squared, that's what we're talking about. Even if my algorithm is sometimes a bit faster or slower, no matter how bad the situation gets or how bad the input is, the performance won't be worse than n squared. I guarantee it. That's what it means. If you look at the code here, and if you look at the chart, you'll see a dotted line. If we call this dotted line n0, actually, when this constant n0 is small, the values or the chart, these two lines cross back and forth. So, what is the x-axis of n? It's the size of the input. And the vertical axis is the time it takes. So when it's less than the constant n0, when it's smaller than n0, the actual execution time, compared to the standard O notation we write, you know what I mean. It can be greater than or less than this value, or fn. But, this. If the input value is indeed greater than n0, what then precisely happens is that the blue line will never, ever go above the red line at any point in time. So, if a time complexity function, which describes the amount of time taken by an algorithm to run as a function of the length of the input, never exceeds n squared, meaning it grows no faster than the square of the input size, then it belongs to big O of n squared. When we say that a function is an element of big O of n squared, it includes functions like these. So, in the case where the largest value is n squared, of course, even in the worst case, it can keep the promise of big O of n squared, because its growth rate is exactly at the n squared level. This is like promising to deliver within 3 days and actually taking exactly 3 days to deliver. So the promise was kept well, but there are some odd ones mixed in here. For example, 3n or n log n. These are faster than n squared. So these are the kinds of functions I'm talking about. These are faster than n squared, so why are they listed under n squared? Going back to the delivery promise, let's say they promised delivery within 3 days, but it actually arrived in just 1 day. Did they keep the promise? Or did they break it? That's right, they kept the promise. These days, when you order delivery, it often arrives even faster than they said it would. That's kind of like big O notation, because it assumes the worst case scenario. And in this case, since it arrived early, there's nothing bad about it. Big O notation is good, too. It's making a promise that its performance won't be worse than n squared. If, in reality, it runs in something like 3n, like 3 times n, which is linear, then that's an algorithm that keeps its promise very well and is excellent. So, big O notation is essentially an upper bound on performance, effectively saying it absolutely won't perform worse than this particular threshold. Since it's for the worst case scenario, algorithms that perform better than that are, of course, included within that promise. Now, let me talk about big omega notation, which is like big O's twin sibling. If big O guarantees the worst case, this one is the exact opposite. So you could say it guarantees the minimum cost, right? It's kind of like saying this. To run this algorithm, you need at least n squared or f of n amount of cost. You have to be prepared for that cost. So maybe it's easier to explain this minimum cost like this. It's kind of like the minimum system requirements for a game. So if you buy a computer that just meets the minimum requirements, the game will run. But if you buy a better computer than that, the game will still run. In the same way, functions that are bigger than n squared, like exponential functions or n cubed, are also included in big O of n squared. Lastly, it's big theta. So, if big O describes the worst case scenario and big omega describes the best case scenario, then big theta is when both the worst and best cases are the same. So it's kind of like a recommendation. Is that the feeling? So you could say this algorithm is ideally designed to have n squared level performance. Even in the worst case, it's n squared, and in the best case, it's also n squared. So based on the baseline and constant standards, it's always bigger than F1, but K1 and K2 are constants, and if you set those constants well, the value will fluctuate within that constant multiple. That's why this is also called tight notation. Then you might have this kind of question. Mathematically, there are a lot of set notations, and the most accurate one is theta. But why is it that in most books or code, people often use the big O equals sign? You might ask that, and that's actually a really important question. If I were to answer it like it's the correct answer or the right answer, in my opinion, it might be because developers just think that being practical is the best. So this is a pretty realistic reason. First, what's most important to a developer is to guarantee that, even in the worst case, the performance won't be slower than this. That's why big O is really important, because it clearly defines that worst case scenario. And another thing is, of course, developers can communicate through books and things like that, but when you're writing code, you leave comments in your code, right? At that time, you note what this code does, what the parameters are, what the return type is, and then what's its time complexity. You want to leave a comment like that, but if you use set notation, like big theta set notation, look at your keyboard. Do you see it on your keyboard? You don't, right? These kinds of symbols aren't on the keyboard. So, when you're leaving code comments, chatting on Messenger, or communicating by email, I think that's why we use the equals sign and big O notation to make things simpler and more convenient. Let's summarize what we've learned today. When it comes to algorithm performance, the choice of algorithm is much more important than the computer's specs. As you can see, especially when dealing with large input sizes, the structure of the algorithm and its time complexity become very important. The language we use to describe how quickly this growth rate increases over time is called big O notation. So, we usually use big O notation to gauge the efficiency of an algorithm. So from now on, when you look at code, don't just think, it compiled and ran, so that's it. Instead, notice things like, there are two nested loops here, and since all of this depends on the input value, at the very least, this would be something like big O of n squared. Think about it in this way. So if the amount of data increases, it might get slower. Being able to analyze things like this means you now have the eyes of a pro. All right, that concludes today's lecture. Thank you for your hard work.